This is Statistics Beautiful, Episode 1. Today, what is probability? What is statistics? What are models, likelihoods, joint and conditional probabilities? All explained in the context of a medical decision problem.
Let's get motivated. Suppose you are a breast cancer doc. What does it mean if your patient has a positive mammography test? Suppose you learn that the prevalence is 1%, the sensitivity is 90%, the specificity is 91%. What is the chance the woman actually has breast cancer?
Well, that's a lot of fancy words.
Prevalence, sensitivity, specificity,
and a lot of mysterious numbers. Stick with me here, folks. You'll get to play with a graphical tool and
find out the answer and why,
and end up understanding the answer a lot better than 75% of cancer doctors.
Who, by the way, don't get it a little wrong, but wildly wrong. Way too big, way too small.
We'll build it all from the ground up. Here we go.
How is statistics different from probability? Well, they both connect a process to some outcome or to data, but they go in opposite directions. Probability is easier to explain. Imagine a process, flesh it out with rules, creating a little world in your mind, and ask, what's going to happen when you kick things off? What will be the outcome of your little world? To figure out the chances of each outcome, well, you can use the mathematics of probability, or you can actually simulate with a functioning model.
Like this one.
Courtesy of the website Maths is Fun. They're UK, so you have to say maths instead of math. Maybe your little world is just catapulting 12 pumpkins and you want to count the outcome to be the number that break. Each time it breaks, record 0. Didn't break, 1. Or maybe you treat 12 patients and you count how many get better. That's cool. You're the little god of your little world created in your brain. You create the pumpkins, you create the patients. But if you do it again, you might get a different count. On repetition, the data come out different each time. And you get to be surprised, even though you know the process because you made the rules. If we kept on going, how many 4s and 5s and 6s and 7s and 8s, 9s, 10s up to 12s do you get? Here, of course, the chance is 50%.
It says so right there on the top.
But boy, that's an awful lot of pumpkins. I mean, patients that are doing just fine. Makes me very suspicious. The data are suggesting that this 50-50 model was wrong. Is that data, 12 out of 12 successes, suspicious enough? That number 12 is our statistic. Statistic, it's suspicious. It's surprising. It's shocking. And maybe it's significant.
Maybe the truth is 5%, 95%, or something else. We'll have to do some statistical analysis.
Let's give it a shot.
We will need
the distribution of all those outcomes. Well, check this out. Now each ball represents an experiment with 12 pumpkins instead of just 1. After 101 experiments, you can see how many of each of these counts occurs. That's how you can figure out probabilities just by simulating. But after 101, there still haven't been any examples of 12 out of 12. Are we supposed to keep on going forever? But if you wanted to know, how often does it occur that
none of those
12 pumpkins break, given that it's just a 50-50 chance? And you had to do this with simulation. That would take a long time. That's where the math comes in. And we'll deal with that later, because with math, you can figure that out instantly. It's just as good as having an infinite number of experiments. Here's just a quick, sexy peek at those equations.
And there's so much more that's hiding here, including mathematicians' favorite triangle, Pascal's triangle. There are lovely links to Pascal's triangle in the description.
We're going to discover that later in the course. Some math notation that you can absorb if you want to. You can skip some of it if you want to.
It's powerful and fun, too.
I'm going to argue later it's good for you, but that's okay. You'll get something out of this no matter what. Let's see. So in statistics, well, that's weird because it's backwards. You don't know the rules. You don't own the world, but you do know the outcome. We call it data. So question is, what process gave the data? We want to learn about the world by looking at the data produced. So we want to make an inference, an educated guess about what the process was. So I think of it as listening to the whispers of nature. Those whispers are the data. To hear and reveal the truth underneath and admit how much you don't know. Analyzing data is a responsibility to be faithful to the voice of nature and understand how much you still don't know even after looking at the data. So let's see how it works. No more pumpkins, no more frivolity. Let's get serious.
We have a doctor's office.
Suppose there's a patient who walks in the door.
Like this guy.
We want to figure out if that patient is still sick or if our marvelous treatment actually cured that patient who is now healthy. No, pumpkins, be gone. Now, we don't know if the patient is healthy or sick. There are two little worlds in our heads, not just one, and we don't know which little world, which process is the truth.
The unknown process
we represent with the Greek letter theta. As you see there, that little set notation, theta is a member of the set healthy and sick.
sometimes called the parameter space. Sometimes the thing that's unknown is called theta, like here.
Theta looks like a unicycle without a seat. Ouch.
Sometimes it's P for probability, like the math formula we saw a bit before. Sometimes alpha, mu, or other Greek letters. Oh, statisticians love them.
Why are they used? I don't know. I only know that I'd like to go to Greece someday and sit on the seaside and maybe sip a little of that ouzo. Yeah. A blood sample is collected for a test. The test can come back negative, probably not the disease, or positive, probably sick, or indeterminate, or what we call here oops, because we don't know what it means. Maybe the dog ate my test tube.
So we didn't get any useful information from the test.
The X is the test result, and that's an observation. X is the result of a process under a particular state of nature, theta, which is the patient is theta equals healthy or theta equals sick. For X in what we're going to call the sample space, this beautiful little rabbit of a capital X here. Going to look like a rabbit? X is not the unknown. It's not like the X-Files. In the statistics direction, which is real life, it's the X that is known, and it's the theta that isn't. Our traditions have everything backwards. Well, that happens.
Of course, sometimes other letters represent data, like S, N, M, A, and Z, all Latin alphabet, which reminds me to go visit Latin America again.
All right. In this table, each row is one of those little worlds. Each row is a model for generating data.
Together, they make a model family.
Each table entry is a conditional probability. Probabilities all add up to 1 in each line because whether the patient is healthy or sick, exactly one result for X has to come back from the lab.
Here, if the patient is sick, the probability that the test result will come back positive is 0.95. I'll bet you're asking, hey, wait, how do we know all those numbers? How accurate are they? Great question for another video. That number, 0.95, has a frequency interpretation. If I perform the test on a large number of sick people, around 95% will test positive. That number is called the sensitivity. It tells us how many of those sick people's sicknesses our test is sensitive enough to pick up. And if I perform the test on many healthy people, around 95% will test negative. That's good. That number is called the specificity because the test is specific for the thing that we want to detect. If you think of oops as just another kind of negative, that pushes the specificity to 97%. Later, we'll find another kind of probability that helps decision making.
We say probability of x given theta. This is a standard notation, and you can see that there is a little bar here. So right there. Whoa, yeah. See, there's a bar in the middle.
And by golly, there's sensitivity and there's specificity. Those are conditional probabilities.
Well, let's see. PR with the curly bracket out front. X given theta equals healthy. If theta equals healthy, the probability distribution is given by these three numbers, 0.95, 0.03, and 0.02. And what you're seeing here is a function or a map or an indexed set where you map from the value of x to the number, value of x to the number, value of x to the number. That's called an indexed set. And in other words, for every possible index x, which for us is positive, negative, and oops, you get that x's probability. And that's what this notation means. I do like it myself. I think it's kind of slick. And it's a nice way of expressing yourself.
Enjoy the freedom of good math notation.
But in real life, you get the test result X, and you don't know what group the patient is in. Maybe the patient is coming from the world of healthy patients, maybe from the world of sick patients. And that's the whole point of getting the test result. Now, each column, it has a name too. That's called the likelihood function. So there's L right there. Likelihood function.
A negative test result was received.
So L
For a negative
is a function from the parameter space to the real line. That's what this notation means. L is a function from theta to the real line. That's how you read that notation. Really? Notation's good. Believe me, people. If x is positive, is observed, we know that, then there are only two possibilities, healthy and positive, or sick and positive, and they live in this column here. Okay? That's called the likelihood function. For positive, the likelihood for healthy is 0.03. Likelihood function for sick is 0.95. It's a lot bigger for sick than healthy. That seems to lean in the direction of this patient is sick, doesn't have the sickness. So the key here is the likelihood function compares explanations for the observation. Could be a true positive, could be a false positive.
And for the oops outcome, the likelihood function is the same for either sick or healthy, 0.02. The likelihood ratio compares the two explanations. A positive could be a true positive or a false positive. A negative could be a false negative or a true negative. And an oops, well, an oops is always an oops.
So you compare the likelihood of the data that you have, the X, if the patient's sick, compared to if the patient is healthy. So if X equals negative, that's 1 here, then this is that ratio. It's about 1 in 32. If it's positive, then it's more like 32.
Which is the reciprocal of 1 over 32.
And finally, if it's oops, then the likelihood ratio is 1, telling you that what you saw, the oops is equally likely whether the patient is sick or healthy. That's appropriate for a lab mistake. Note that in the context of likelihood, these numbers, each column, don't add up to 1. 0.95 and 0.03 is 0.98.
0.02 and 0.02 equals 0.04. So they can't mean probability of sick and probability of healthy because they don't add up to 1.
But we're going to fix that
now. Okay, Doc. One of your patients walks in the door. One look and you decide the chance that patient has your favorite disease is 1 in 10. We say that the prevalence
of the disease is 10%. What does that mean, prevalence?
It might mean that you have great statistics on exactly this kind of person. Or it might mean you have great experience and instinct, which gives you a gut feeling, and that's how you'd be willing to bet 9-to-1 odds that the patient doesn't have the disease. And what that really means is
we need more information.
Well, yes, let's do that medical test. Find out what X is, but before that,
where did the patient come from? From another doctor's office where they don't like sick people.
Or people without good health insurance.
And they send them all to me? Well, maybe the prevalence then is high. Or from a flyer in the grocery store where almost everybody walking by is healthy.
Promising free CBD lollipops.
Well, then the prevalence is probably very low.
This guy, mostly here for the lollipops. But our guy has a prevalence of 10%
probability of sick. Right here.
Together with the probability of healthy, it constitutes the prior distribution of theta. Prior means prior to knowing the data, the test outcome X.
So we get a big boost in understanding if we also know the prevalence. It's a proportion of people walking in my clinic door who actually do have the disease.
Because it's going to be a key ingredient in making the best medical decisions for future treatment. The prior distribution is an example of a marginal distribution. We'll learn about another marginal distribution, a very important one, shortly. Let's see what happens when you multiply the model rho for X given healthy times the probability of healthy. You get the probability that both the patient is healthy and the test result is X. Likewise for theta equals sick. Putting it together row by row, our original model family times the prior or marginal distribution of theta, the unknown patients group. Oh ho, look what we get.
The joint distribution of theta and X.
Conditional probability times marginal probability equals joint probability. Now when you add across, instead of 1 and 1, you get 0.9 and 0.1. Along the right margin. Aha!
Then add down 0.9 and 0.1, you get 1. Or you can add the columns.
To get the bottom margin,
then add the column totals, you get 1. Either way. The 6 combinations of X and theta, all 6 of them,
their probabilities will
add up to 1. It's the magic of arithmetic. So, for example, this joint probability that theta is healthy and X is positive is equal to 0.027, which you can see right there.
That is called a false positive. That bottom marginal distribution means something important. It is the distribution of the test results, the 3 X values, negative, positive, and oops, adding across the 2 patient groups. But what if I got the test result already? Then its probability is 1. And the other 2 X's, their probability is 0. Sure, other patients, other days, other test results. But right now, we only care about this patient. So we will condition on what we know. That means we divide by its probability. That was the idea of the Reverend Thomas Bayes, a guy
that lived in the 1700s.
He was, no joke, officially a nonconformist reverend. Another Bayes innovation was his definition of probability of an event as, and I love this, the ratio between the value at which an expectation, depending on the happening of the event, ought to be computed, and the value of the thing expected upon its happening. What the heck does that mean? And why am I talking like this? Anyway, the word ought jumps out at you. It suggests making the right choice in the face of uncertainty. That craziness we will unpack in a future episode. He died 2.5 centuries ago, and yet his name absolutely blankets the literature and the conferences in statistics, computer science, artificial intelligence, economics, bioinformatics, you name it, his name, it's Bayes everywhere. But his ideas really came to fruition only in the last few decades with the advent of incredible computing power.
Quite a story.
So, before we had conditional times marginal equals joint. Now we already have the joint distribution. We'll divide it by the other marginal to get a different conditional distribution. Joint divided by marginal equals conditional. The result, it's called the posterior probability because it's posterior to, that is, after learning what x is. And that's going to be exciting because
That's when we're beginning to be able to use probability to make good decisions and influence the world.
And looky here, now each column does add up to 1, and each column is a probability distribution.
If you ask what is the probability that the patient is sick, given that a test result is positive, well, given that the test result is positive means you're in the second column here. Okay?
So given what I knew before, the prevalence, plus what I know now, the data x, combining those two sources of information together, my current belief is that there is a 77.9% chance that the patient is sick. That's right here. This posterior
Probability table combines the two types of probability, belief and frequency, in one table.
And that's what we've been after all along. Posterior probability, or as the French say, probabilité derrière. Now we'll pay a little visit to the land of Oz. No, the land of odds. Decision makers, for example doctors, are gamblers, and gamblers need to think about odds.
The key concept, a little bit more math. Here's a function, odds. Like usual, the colon is
Red.
as is a function from. So odds is a function from what this is the set of numbers between 0 and 1, including the endpoint 0 and 1, to the set of numbers between 0 and infinity, and again including the outsides, the 0 and the infinity. That's what square brackets mean in the mathematical lingo. And so it's read as the odds is a function from the unit interval to the extended non-negative real line. It's fun to talk like that, I have to admit. And the odds
Function works.
like this. If you give me a probability p, I'll give you a number that is p divided by 1 minus p.
Here's a plot of the odds. So if you put in a p, out comes the odds. If you put in a p of a half, 0.5, the odds are 1 to 1, or 1. If you put in a p of 0.9, 90% probability, that's 9 to 1 odds, and the odds equals 9. That person who got a positive test result had a probability of being sick of 0.779, and that translates into an odds of 0.779 divided by 0.221, and that is equal to 3.5. Before the data, it was 1/9, which meant you'd need a payoff of more than 9 to 1 to make it worthwhile to treat a patient without even doing a test. After this positive test, to justify not treating this person with a positive test, now the badness of treating a healthy person would have to be 3.5 times or more worse than failing to treat a sick person. Let's compare the odds of having the disease before a test result, the prior odds, with the odds you get after observing a negative or a positive or an oops result. Here we see that the observation x equals negative lowers the probability of sick and x equals positive raises it. Observing x equals oops does not provide any information as reflected in the likelihood ratio. Aside from gambling, another great thing about living in the land of Oz, the land of odds, is it plays nicely with the likelihood ratio. Even easier than going from model family to joint to posterior and finally to odds, just multiply the prior odds times the likelihood ratio. Boom! Done! Let's recap. We started with a family of conditional probabilities, the model family. We multiplied it with a marginal probability distribution, prevalence and 1 minus prevalence. That gave us the joint distribution. Then we divided by the column totals, which constitute another marginal distribution for the 3x outcomes. We ended up with another family of conditional probabilities, the family of posterior probabilities. The joint distribution is the product of marginal probability times conditional probability. We just used both of those ways of factoring the joint distribution. Didn't I promise that these posterior probabilities will help us make better decisions? I sure did. If the patient is sick, you probably want to treat. If not, you probably want to hold off, what the doctors call watchful waiting. Now that we have the test result, we have the posterior probability of being sick. But to make the best decision, you need one new ingredient. You have to know or guess at the costs of making 2 types of mistakes. Given the healthy person the treatment when they should be just watched. And given the sick person watchful waiting when they should be treated. We will leave the details for another episode, but for now, start with giving both costs a number and boil them down to the ratio of the 2 costs. We'll call that ratio R. The key idea is that you should treat the person if the posterior odds is bigger than R, otherwise give them the good old watchful waiting. The best decision depends on the prevalence. If the prevalence is too low, even a positive test isn't enough to justify treating the person. So doctors must be pretty darn good at figuring out these posterior probabilities, right? Well, check this out. Gerd Gigerenzer and colleagues asked 160 gynecological oncologists, breast cancer docs, what to do if a woman has a positive mammography test, and this following information is present. The prevalence is 1%, the sensitivity is 90%, the specificity, or 1 minus the false positive rate, is 91%. What is the chance the woman actually has breast cancer? The choices are A, 81%, B, 90%, C, 10%, and D, 1%, the same as the prevalence. Wow, those choices are way all over the map. Even with a positive test result, the answer is C, about 10%, because of the low prevalence. How many of those professionals got it right? 21%. Not even a quarter, which you'd expect if they were just guessing. Actually, hey, that's worse than just guessing. Gigerenzer's team gave the doctors training, and they improved markedly from 21% correct to 87%. The training was, let's say, somewhat effective. There's a link to his great article in the description. To do the training, they left behind the lingo of probability on the left side of this diagram and went with a visualization of the same information as a picture of 1,000 people and what the subgroups are on the right side of the diagram. Much easier to grasp for most people. Better than talking about fractions of a woman, picture a group of 1,000 women and let the scenario numbers tell you how big the subgroups are. Then the fraction will be 9 over 9 plus 89, or roughly odds of 1/9. It turns out that years later, Gigerenzer's idea inspired me to find a way to design biomarker studies to help doctors zero in on what makes a biomarker clinical useful. Another link in the description for you. Let's examine this in light of deciding whether to treat a patient with a positive mammogram. Here's the Gigerenzer setup right here. Prevalence, sensitivity, specificity, and of course the observation is a positive mammogram. Plus, for the sake of illustration, suppose that the penalty ratio is 10, so it's 10 times worse to miss the chance to treat a person with breast cancer than to treat one who shouldn't be treated for cancer. This interactive webpage shows you the relationships among all these ideas. What affects the choice of treating the patient versus watchful waiting at the blue line representing the scenario's prevalence of 1%. The treat line and the wait line cross. Here the treat option and the wait option are equal in expected loss. At higher prevalence, you see the T's are below the W's. Definitely treat. At lower prevalence, the W's are below the T's. Don't treat. Wait. Watchfully wait. Other ways to make the treatment action the best action include raising the sensitivity or specificity, or raising R by raising the loss of a false negative, or lowering the loss from a false positive. Raising the specificity is much more important than raising the sensitivity. You can play around with the scenario yourself. A link to this page is in the description. There will be a guided tour in a later video focusing on decision making. When it's ready, I'll add a link to the description below. But hey now, what if we have more than one piece of data? Say another test, or the patient's age or sex. How do we combine information to make an even more accurate decision? And what can go wrong? Coming in our next exciting episode. Together with a look ahead to exotic topics like conditional independence, causal analysis, Markov chains, and powerful computing methods. In the meantime, while you wait, listen to some Professor Beautiful elevator music. You won't hear it on an elevator, but it might elevate you.